So this is Pratibha Ramponda. So today we are going to discuss your unit 2, that is bipolar transistors, which is known as BJT. So the contents which we are going to study over here is introduction, types of transistors, transistor biasing, working of transistors, transistor connection, relation between alpha and beta, characteristics of transistor configuration, transistor as switch and amplifier, thermal runaway. So coming to the introduction, transistor basically it is a device which will transfer a signal from its low resistance to high resistance. So it is also said that a transistor is a 3-terminal device, 3-layer, 2 PN junctions formed by sandwiching either one p-type between two n-type or one n-type between two p-type semiconductor. So as I said that your transistor is a 3-terminal device. The 3 terminals are emitter, base, collector. So when we are speaking about emitter, it is a first section which is supplying you the charge carrier. So those charge carriers can be either electrons or holes. It is called emitter, and this section is heavily doped when you compare it to the other two terminals. The second is base, which is the middle section of transistor. This forms a PN junction between your emitter and collector. This is very thin and lightly doped. The third is collector, which is the third terminal of a transistor which collects the charge carriers, and it is physically larger when you compare it to the other two regions. Coming to the types of transistors, basically there are two types of transistors. One is NPN and one more is PNP. So what is NPN transistor? NPN transistor is composed by one p-type sandwiched between two n-type. So the structure, can you see here the structure? The three regions NPN. For N we have emitter, for P we have collected base, and for N again there is a collector. So this is the structure of your NPN transistor. Symbolically you are going to represent your NPN transistor in this way, but make sure that how is the current flow direction shown over here. You can see this is NPN. Your current always flows from positive to negative. So this is P and this is N. So the current is flowing from base to emitter. So this is all about your NPN transistor. Coming to PNP transistor, when we are defining PNP transistor, so it is a transistor where one n-type is sandwiched between two p-type semiconductors. So you can see the structure over here is P is connected to your emitter, N is connected to base, and P is connected to collector. The symbol remains the same, but the flow of the direction changes, because now here emitter is having p-type, base is having n-type, and collector is having p-type. So I said you that current always flows from positive to negative. So here the collector is flowing from emitter to base. So these were the two types of transistors. Now what is transistor biasing? Biasing is nothing but it is applying a proper DC voltage to your device, is called biasing. So there are three ways of biasing your transistor, or you can also say them as modes of transistor operation. In that, the first one is forward active mode. Now in this forward active mode, you can see that this is your NPN transistor, where this is emitter, for P is connected to base and N is connected to collector. So here there are two junctions. The two junctions are emitter base junction and base collector junction, or you can also say collector base junction. So in forward active region, your emitter base junction is made forward bias and your collector base junction is made reverse bias. How? Now when you connect your N to your N of your voltage and P to your positive of your voltage, we say that this junction is forward bias. And when we connect P to your negative of your voltage and N to your positive of your voltage, we say that this junction is reverse bias. So for forward active region, you should remember that your emitter base junction is forward biased and your collector base junction is reverse biased. The next region is saturation region, where your emitter base junction and your collector base junction both are forward bias. So again this is your NPN. So for forward bias, what is the condition? You have to connect your N to your negative of your voltage and P to your positive of your voltage. Again here this is also forward bias, so P is connected to positive of your voltage and N is connected to your negative of voltage. So this is the reason or the condition for your saturation region. The next is cutoff region. So cutoff region in which your both emitter base and your collector base are reverse bias. How is that? When N is connected to positive and P is connected to negative. Here P is connected to negative and N is connected to positive. So this is the conditions for your cutoff region. It is seen that your transistor will act like a switch in your saturation and cutoff region, and your transistor will act like a amplifier when it is in forward active region. So this is all about your transistor biasing or transistor modes of operation. The next over here is transistor working. So first we will see NPN transistor, how it works. So what are the condition is, you can see this is NPN. N is emitter, P is base and N is collector. Now here your emitter base junction is forward biased and your collector base junction is reverse bias. How it works? Whenever it is made forward bias, this negative, and in N region electrons are majority carriers. So this negative and this negative, they repel. So these all electrons which are present in your N region, they start moving towards the P region. So in P region there are holes, but because it is lightly doped there are only few holes. So whatever the electrons which are moving towards the P, only 5% of electrons will recombine with the holes. So the remaining 95% of electrons, they move towards the collector current. So here the 5% which electron hole pair is present, they will constitute the base current. The remaining 95% will constitute the collector current. So the total emitter current will 100% will be equal to what? 5% of your base current and the 95% of your collector current. So this is how your NPN transistor works. Now when we are speaking about PNP transistor, you can see that here emitter is connected to P, base is connected to N, again P is connected to your collector. Now here your emitter base junction is made forward biased and your collector base junction is made reverse biased. So now this is positive and majority carriers in your P type are holes. So holes and positive start repelling. So all the holes come and come towards the N region. Now here, because it is base is lightly doped, there are less number of electrons. So only 5% of holes they will combine with this electron and 5% of your base current is formed. The remaining hole, they will move towards the collector current. So that will provide a 95% of your IC current. So total I will be equal to IB plus IC. So this is how your NPN and PNP transistor works. The next is transistor connection. Basically, you can connect your transistor in three ways. One is common base connection, one more is common emitter connection, and the third is common collector connection. So you can see this is your common base connection. Common base means you are making your base common to your both emitter and collector, and you are putting your, or you are giving your input across your emitter base junction and you are taking your output across collector base junction. So this is how with the help of symbolically it has been explained. Now when we are speaking about common emitter connection, in the sense you are making your emitter as common for your both base as well as collector. So here input is applied between your base emitter junction and output is taken across your collector emitter junction. The third is common collector connection. Common collector in the sense, now here you are making your collector common to your both base as well as your emitter. Okay, so here your input is always applied across your base collector junction and your output is taken across your collector emitter junction. One note over here is, in all these connections your emitter base junction will be always made forward bias and your collector base junction will be always reverse biased. Next is current amplification factor alpha and beta. So this is current gain, which is known as alpha. So this is defined as the ratio between your collector current and emitter current, and beta, that is your current amplification factor, it is a ratio of your collector current to your base current. So there is a relation between your alpha and beta. How to find this? We know that your emitter current is equal to your collector current plus base current. So you have to divide this equation by IC. So when you divide it, this IC gets cancelled. So this will be I is upon IC is equal to 1 plus IB upon IC. So we know that current gain alpha is equal to IC by and current amplification factor beta is equal to IC by IB. So what you can do is you can just replace. Now here I by IC is equal to what? 1 by alpha, and IB by IC is equal to 1 by beta plus 1. Take the LCM. So this will be 1 by alpha is equal to 1 plus beta by beta. So in this way alpha will be what? Take the reciprocal of this. So it will be beta by 1 plus beta. So when you cross multiply it, you will get in this form. Alpha is of 1 plus beta is equal to beta. So multiply this alpha in this bracket. So alpha into 1 is alpha plus alpha into beta is alpha beta is equal to beta. So bring the beta term this side. So your alpha you keep this side here itself. So this beta is over here. This plus alpha beta, if it comes this side, it will be minus alpha beta. So take beta common in this. So alpha is equal to beta. Inside the bracket it remains 1 minus alpha. So from this beta will be what? Alpha upon 1 minus alpha. This is not 1 plus alpha, it is 1 minus alpha. Please note it. Next, there are some small problems. So you can see here the problem says that here is a transistor which is having beta as 200, collector current is 20. So they have asked you to find the emitter current. So we know that beta is equal to IC by IB, and from this what will be IB? IC by beta. You have the value of IC, you have the value of beta, you will get the value of IB. Now you want to find I. We also know that I is equal to IC plus IB. So you have the value of IB, you have found the value of IC. Sorry, you have the value of IC, you have found the value of IB. When you substitute, you will get the I. In the same fashion, this is also problem. Next is characteristics of transistors in your CB configurations. The first is input characteristics. You can see that your IE is taken along y-axis and VB is taken along x-axis, and VCB is kept constant. So your current will be almost zero, or it will be increasing slowly until it reaches the knee voltage. So the knee voltage for your silicon is 0.5 volt and for germanium it is 0.1 volt. After that your current almost goes on increasing by keeping your VCB constant. So it is also seen that whenever you change your VCB, your curve goes on shifting. Okay, so if for VCB 10 volt, the curve remains like this. If your VCB is changed for 5 volt, the curve will shift. So these are the input characteristics. So if you want to define the input resistance, which is denoted by Ri, will be equal to change in your VB voltage divided by change in your I voltage by keeping VCB constant. So basically your input resistance will be very small. Coming to the output characteristics, you can see that the plot is IC versus VCB by keeping I constant. So there is a cutoff region. When your current I is equal to 0, still a small current of IC is flowing, but this current is negligible, right? It is almost equal to 0. So it is acting like a cutoff region. So whenever you are increasing your whenever you are increasing your VBE, your IC remains almost constant at your I. So your output resistance can be denoted R0 is equal to change in your VCB upon change in your IC by keeping IE constant. And your output characteristics, your output resistance will be high. Next is characteristics of transistor in C configurations. So here the input is IB versus VBE by keeping VCE constant. Here also your almost current is 0 until it reaches your knee voltage, that is 0.5 volt for your silicon and 0.1 volt for your germanium. This particular is for your germanium. So after that your current goes on increasing by keeping your VCE constant. So when you change your VCE values, your curve will be shifting. The next is output characteristics. So here you can see that your IC is taken along y-axis and your VC is taken along x-axis. So there is a cutoff region, okay, where a small leakage current flows, but this is neglected by keeping your IB constant. Now here you can see that your IC current will increase with the help of your VCE, but that occurs only between 0 and 1 volt. That particular region is known as saturation region, and after that your current almost remains constant, and that region is known as active region, and where your almost current leakage current is occurring, which is 0, it is known as cutoff region. So this is all about the output characteristics. The next is how transistor is used as a switch. So you can see that your transistor will work as a switch in your cutoff region and in your saturation region. So if we are speaking about cutoff region, what are the conditions? Your emitter base junction and your collector base junction both are reverse bias. So when you are making your emitter base junction reverse bias, in the sense it is open switch, so your transistor is in off state. Cutoff means it is in off state, so current does not flow. So whatever the output over here will be equal to VCC what you are applying. So Vin is equal to minus V1, that is when it is reverse biased. When your emitter base is reverse bias, your transistor is off because it is in cutoff region. So your output V0 will be high. High in the sense VCC, if it is 5 volt, that V0 will be equal to 5 volt, but your switch will be in off state. Now when you apply Vin is equal to plus V2. Plus V2 means it is forward biased. So when this emitter base junction is forward biased, your transistor is on. So when your transistor is on, your V0 will be what? Whatever the input you are applying, that, right? So that time it will be low when you compare it with your VCC, but your switch is on. Clear? So this is how your transistor is used as a switch. The next is transistor circuit as an amplifier. So this is base emitter junction and this is collector base. So base emitter you are applying the input and collector emitter you are taking your output. So here you can see when your input, whatever the input you are applying, if it is having low resistance, the change in this voltage at your input side will give rise high current in your collector current, and because your high collector current, high voltage will occur across your resistance RC. In the sense, now if you are applying 2 volt of input voltage, at this you will get 4 voltage. So that is nothing but your small input current is amplified to a larger output voltage. Okay, so this is how your transistor circuit is used as a amplifier. The next is thermal runaway. Now what is this thermal runaway? Because of your high temperature or increase in your temperature, your transistor gets destructed, and this is known as thermal runaway. How you can avoid this? By heat sink. Now what is this heat sink? It is a metallic heat conducting device which is placed in contact with your transistor in order to dissipate heat. By using this heat sink, you can control your transistor from your thermal runaway. Thank you, students.